Those
Muscle
are muscle
tissue.
cells. What kind of muscle cells?
Heart.
Yeah, it's pretty easy, right? Okay, so today we are going to have a discussion about EKG some more. In fact, I'm going to kind of start over but go really, really fast over the stuff we've done already, just as a way of reminding you and reviewing, and then we'll move on. And then we'll talk some excitation, contraction, coupling, and some other good topics. All right. So ECG, EKG. Last time I started to tell you about this. What was the principle I was telling you about? We're not actually measuring the state of depolarization and repolarization of the cells, are we? What are we measuring? The what? The movement or the wave of depolarization or repolarization. Okay, so it's not absolute. So if these cells were at 90, minus 90, or they were at minus 70, or minus 50, or plus 30, and held to that value, it wouldn't appear on an EKG. It's the change that we can sense. Right, so when we put an EKG on a patient, what we're doing is we're really detecting those movements of depolarization or repolarization waves. Okay, they're sort of pushing their way through the body, and on the tips of your fingers and your toes, all over the surface of your body, we can sense the movement of ions throughout your body. Okay, so the heart's coordinated activities can be sensed at every extremity of your body. Okay. All right, so in basic principles, I've got this block of cells here, and we talked about how there's no response. We don't see anything if we've got a chunk of muscle cell that's not doing anything. Okay, minus 90, nothing's happening. Okay. If we have a depolarization wave that's moving, and what's critical here is that it's moving towards one of our electrodes, we're going to have a wave. Okay. And the way that this appears on an EKG is that we're going to see if a depolarization wave is headed towards that positive electrode, we're going to have a positive deflection of the EKG. Okay. What do you suppose would happen if it was moving away from the positive electrode? It would be moving downward instead. Okay. So a depolarization moving towards the positive electrode means that we have a positive EKG. Okay. Once it's fully depolarized, once all of these cells have depolarized, let's say they're at plateau, right? Plus 30 or something like that. What's going to happen now if once everything is depolarized? Is it going to, what's going to happen? It goes back to neutral, right? So it doesn't go below, it goes back to where it was, okay? It just returns to where it was and everything's fine, okay? So if we looked at a depolarized mass of cells or a polarized mass of cells, it would look the same on EKG, okay? It's the change that we sense. All right, so here it's returned back to normal. Okay. Now, what if we have, instead of a wave of depolarization heading from left to right, we have a wave of repolarization? Okay. We have a wave of repolarization. What's going to happen? It's going to go downward, negative. Okay. So depolarizations moving towards the positive electrode result in a positive wave. Repolarizations headed in the same direction give us a negative wave. You believe me? Yes. Good. All right, so if we want to sort of think about the possibilities here, right? If we've got a depolarizing wave heading towards our positive electrode, or if we have a repolarizing wave heading away from it, these are going to give us positive EKGs. Okay. And what's going to give us a negative change, or a negative EKG, is that if we have a depolarization headed away from that positive electrode, or a repolarizing wave heading towards it. Okay? So, commit this to memory. This will help you understand EKG. This is sort of the nuts and bolts of understanding why a wave is positive or negative. Okay? And remember, once that wave has passed, and there's no more change in our cells, then we're going to have either a return to baseline or it's going to stay at baseline, right? So the return to baseline just means that we now no longer have a positive or a negative influence on that EKG. Okay. You feeling okay with this? Most of what we're going to be talking about are depolarization waves. Okay. Repolarizations obviously happen in the heart, but sometimes they're a little bit less organized, so you don't see them as much. So we'll mention it, but mostly we're going to talk about depolarization waves to understand what we see in an EKG. Okay, so a couple other principles here. At the top here, we're looking at a depolarization wave headed towards our positive electrode. So as expected, we have a positive EKG on the right. Okay. But what if it's not headed directly at it? Okay. What if it's headed at an angle to that positive electrode? What do you see? What's going to happen? We're going to get a smaller wave than if it was directly headed towards it. Okay. This is really important because when we do EKG, we can't align our electrodes exactly with every electrical event of the heart. Right? Some of them we see really well, and others we don't. Okay. So it's sort of like what we have here is our positive electrode is kind of this is our eyeball, right? And we're looking at eyelashes. Here we go. We are looking straight ahead, okay? And if we're seeing something that's actually moving this way, what we really only see is the dimension of it that's headed towards us, okay? So for every one of these black arrows that I'm showing you, we can call this a vector, right? And who's getting a little bit of creepy feeling from physics out of this? Okay, just push it down. Don't think about it, okay? But what is a vector? Somebody? What's a vector?
So the vector quantity is something with direction and magnitude.
Right, we're describing something's direction and magnitude. Okay, for the moment, let's just talk about its direction. Okay, so we're looking from positive to negative along that axis. Okay, so in terms of its direction, we see a component, right? It's mostly headed in that direction, but not entirely. Okay, so we can divide that vector. We can take it apart into two components along the axis that we're looking at, right, and a perpendicular axis. So my two green arrows are basically saying, all right, we've got a vector here that has a certain amount of horizontal magnitude, okay, and a little bit less, but some vertical magnitude. Okay, so when we turn our little block of cells here, and the depolarization is traveling along this black arrow's vector, okay, we can see a component of that directionality. Okay, but what do we see? We see it at a magnitude that's a little bit less than its actual magnitude. Okay, we see absolutely no bit of its vertical dimension, right? Because we're looking horizontally. Okay. Are you with me? If I promise no more physics, are you with me? See? Yeah, okay, that's so hard. All right, there's more physics. Not a lot, though. Not today. Okay, so just keep this in mind because whenever we're looking at EKG waves, like I said, we're not very often, we're very infrequently looking directly along the axis of these waves of depolarization. Okay. Another thing, magnitude, right? We have at the top a mass of cells undergoing a depolarization. At the bottom, we've got a bigger mass of cells undergoing a depolarization. Okay? The magnitude of the individual cells depolarizations is not any different, but in total, right, we have more cells undergoing this change, so that the overall effect is that we have a stronger wave of depolarization. Okay? So instead of making a little ripple through the ionic environment of your body, you make a big ripple or a small wave. Okay? So how does this appear on EKG? Well, the more cells that are involved, okay, so think ventricles compared to atria, right? The more cells involved, the more these waves will represent themselves on an EKG. Okay. All right, so that's it. Now you know everything. Yes?
So in the last slide, does that mean that the vertical component isn't reflected at all in the
Right. Right. So the vertical component is not represented. Right. So basically subtract that out of what appears on the EKG. Okay. And in fact, if there were a vertical component here, let's say we had another vector traveling, just to make, so if we had a vector like this, it would look the same, only a little bit smaller, right? Same, only smaller, even smaller. And at this point, if it were perpendicular, there would be no wave whatsoever, okay? So if the wave of depolarization is traveling perpendicular to the axis of the EKG, you see absolutely nothing, okay? So EKG has the ability to see electrical movements, electrical waves, so long as they are at least a little bit pointed in the direction of or away from an electrode. Okay? But if it's perpendicular, it's invisible. Okay. Any questions about this? I mean, this is kind of weird. And, I don't know. It's weird. There's no cells. There are cells, but yeah.
If the vector was like shifted and it was also a larger mass, would they kind of cancel out when it was
Sure.
normal?
A vector of one size might appear on an EKG to be identical in size to one that's pointed away but is of greater magnitude.
Okay.
Yeah. Sure. Okay, with those principles in mind, let's talk about what happens here in the heart. And you guys in the lab, you're going to get more exposure to this, but this is sort of a get up to speed on EKG. All right, so what do we call this axis that we're sort of looking down this little dotted line here? We call this a lead. Okay, so an EKG lead is a particular viewing perspective. Okay. There's lots of different leads we could use. One of the more common is what's shown here. You could put an electrode anywhere on your arm. This is what you look like. This is your arm. Put on your wrist, on your elbow, that'd be weird. Shoulder. Doesn't matter. It's where it connects with the rest of your body that matters. So that point here is where our negative electrode is. Okay. Usually put it on the wrist, especially in lab, put it on your wrist. Okay. And the other can go on your ankle on the opposite side. Okay. Could go on your ankle, shin, knee, thigh. It's all going to look the same because it's where that connects to the rest of your body. Okay. So, in other words, moving your arms and legs with electrodes attached is not going to change your EKG, except all movement affects EKG. Okay. All right. So that's what a lead is. Now, here's the one we'll use for the purposes of illustrating what the heart is doing. In fact, this is a pretty common one. There are other ways to look at the heart. You can look at it instead of across the body. You can look at it through the body. So you can have electrodes on your chest and look cross-sectionally through. And the point of EKG is that it's a diagnostic tool to tell you about the electrical activity of the heart. Okay, so first things. The first thing that happens is the atria depolarize. Actually, what happens before the atria depolarize? What other thing depolarizes first? The SA node, right. Okay, so the SA node is a tiny, tiny, tiny cluster of cells. The SA node does not appear on EKG because it's a tiny, tiny cluster of cells. Okay. But the effects of that can be seen in the atrium. And the atrium has this, all of these little cells are connected through gap junctions, right? So what happens is that starting at the SA node, somewhere in the upper left of our figure here, we're going to have an action potential that spreads throughout the atrium. Okay? And how it spreads is very predictable. Okay? All these little black arrows show you the directions that this action potential is spreading. Okay? So these are all little tiny vectors. Okay? Where's my black arrow? There it is. Sorry. So all of these little black arrows represent the little vectors of movement, or in other words, the main paths of action potentials through the atrium. Okay? But what we can do with vectors, remember this is just describing the magnitude and direction of these waves of depolarization, is that we can add them together. Okay? So when the time expires from this room, right, everybody's gonna leave through a different direction, right? Some of you are gonna head up that way, some that way, some across the front of the room, and others that direction. But on average, we can see the overall effect of all of you heading in slightly different directions is that you're all gonna be headed that way, right? And we can sort of sum all of your vectors to come up with an average direction and magnitude. Okay. And so that's what this little green arrow is representing here. All right, we've got some downward movement, some leftward movement. Remember, left is 2, right? And how does this compare to our lead? How does this green arrow, this vector, compare to the lead? What would you say about it? Is it in the direction of the lead? More or less, right? If it's perpendicular, we're not going to see it. And if it's pointed towards the negative, it's going to be a negative wave. But in fact, it's pointed towards the positive. Okay? And so what we see from that perspective of the positive lead is that we have a small positive EKG deflection. Okay? The wave goes up. And when that wave of depolarization ends, the wave comes down, back to normal. Okay? So it's not the whole wave exactly that is the depolarization, but it's the increasing part of it, right? The first half of it. But for convenience sake, we sort of, in a shorthand way, say the P wave, this little lump here, corresponds to atrial depolarization. Okay. Easy? Nothing to it. Okay. So that's the simple part. We have a P wave corresponding to the atrial depolarization, right? So this vector is headed towards the positive, and that's why we see a positive P wave. Okay? Any questions? So the EKG doesn't, it's responding to all these little individual vectors, but it's sort of averaging together in the way that my arrow represents the average. So where would the, so this is happening in time. Where would the SA node fire off its action potential? Remember, it's not shown here, but where would you find it? Where would you expect to find it temporally at the same time? Over here? No. So right about here, right? That's what you'd expect. That's where the SA node would be setting off its action potential, okay? If we're just using this as a time scale, okay? But remember, we're not going to see the SA node here because it's too small of a depolarization to affect the EKG. Okay, all right. Those action potentials are going to travel through these atrial cells and the internodal pathway, and ultimately we're going to have an action potential arrive at the next part, which is, what's the next part of the conduction system? AV node. Right. AV node also doesn't appear. Okay. So from the SA node to the AV node, we've got electrical activity. Really the only thing that shows up on this EKG is going to be the contractile cells because they're the most numerous. Okay, so that's your P wave. Lots of different leads are possible. Right arm, right leg. Right arm, left leg. All kinds of things are possible here. These are some common ones, all right? And which of these would you expect to find the P wave have the greatest amplitude? Which of those leads? They should name them better, right? Charles, Anna, Frederick. Which one of these, so the green arrow represents the direction of our atrial depolarization vector. Which lead would you expect to see the biggest amplitude? The one that's at 30 degrees, right, negative AVR. Where would you not see it at all? Where would it be invisible? Which one? 3, yeah. So if you had your positive electrode down here and your negative here, or vice versa, it doesn't matter. You wouldn't see the P wave, it'd be invisible. Okay? But as you get closer and closer to that vector, it's going to get bigger and bigger. Okay? Does that make sense? So different vectors are useful for seeing different things on EKG, which is why we don't just have one. Okay. All right, so this is the fun part. The ventricles are a little bit complicated, and I'm going to make it as simple as I can. Do you have a question? Yeah. Sorry about that.
The other slide, why not 90? Since it's perpendicular,
90 is not quite perpendicular. The one that's the most perpendicular, well, at least I haven't pulled out a compass. Well, I think that's pretty perpendicular with that.
Oh.
See what I mean?
I was just thinking.
So you have a right angle
Okay.
here. Does that make sense? At the 90, you'd see a small part of it. It'd still be P wave, it'd be very small compared to if you're looking at the 30-degree angle. Okay. So, all right. So let's take a look at the ventricles. I removed the atria because I didn't draw this picture. So what we have here, I don't know if you can see them very well. I hope you can. If you look maybe at your own slides, you'll see it better. But there's a little arrow here, and here, and here, and here. See those? Okay. So what happens is that the ventricles, being such a large mass of cells, do not all simultaneously undergo depolarization at once. There's a pattern to it. Okay? So the way that it works is that it starts. What's this little chunk of tissue here in the middle that's looking green and yellow? You know what that is? What would you call that thing? Yeah, that's the interventricular septum, right? This is your left ventricular wall. Here's your right ventricular wall. Down here's the apex. Okay. So the interventricular septum has a particular part of the conduction system. That's called the bundle branches. Okay. There are bundle branches that run down right and left. Okay, one goes primarily to the right ventricle, the other to the left. But what happens is that in almost every human heart, the way this works is that those bundle branches, as they're traveling down the interventricular septum, stimulate those interventricular septal cells. Okay, and the way that it works is that the one traveling on the left, over here, happens to stimulate the septal cardiac cells. Okay, but the one on the right just passes through and doesn't stimulate the cells. Okay, so we get a vector that's moving. Let me just make this a little bit larger so you can sort of see. It's moving in that direction. Okay, and then you get another one as the action potential spread over here. Now, it's also spreading over in this direction, but since the left ventricular wall is so much thicker, we get a much more robust response here. So if we, again, take all the individual tiny little vectors and add them together, the result is that we have a vector in this direction that is towards the left. Okay. And then finally, the very tops of the ventricle are depolarizing. Okay, but again, left side is bigger, and we have more of a response. Okay, so the way that this works is that it's, if you think in terms of directions, the heart is kind of angled a little bit down towards the left, and if you put a clock over this, it's not exactly, but it's sort of 9 o'clock, then 5, then 2, then 1. Okay, those are sort of the vectors that are occurring throughout the ventricle's activity. Okay, so you can see why we have a little dip, right? This thing here is called the QRS complex, right? See that little green dip downward? Can somebody explain why it's moving downward? Yeah. Right, it's a depolarization, and to make this arrow bigger, it's a depolarization, and it's heading more to the negative electron than the positive, right? So depolarization towards positive EKG. Depolarization towards negative EKG. Okay. And you can see that it's not a lot towards the negative, right? But just a little bit, and that's why we have such a tiny little wave. Okay. Any questions about that? Yeah.
Can you explain why the green vector, I mean, why does it go to the left? Why it goes to the right?
Why does the green part go to the left? In the heart you have, so let me illustrate this. So this is your heart, this is your interventricular septum here, and this is the wall of your heart. Okay. The bundle branches are traveling down like this, and then they become Purkinje. Okay. These bundle branches are connected to the cardiocytes in the septum. Okay, on the left, this is the left side. Okay, the right side is not connected. Who thought that was a good idea? I don't know, but that's the way it is in almost everybody. Okay. So what happens is that when they have action potentials, they're spreading in this direction, from left to right. Yeah. we won't get into a person whose heart's on the wrong side of the body. That's, everything's the opposite. But it does happen. And even if your heart's on the correct side of the body, no offense, if you have levocardia, anyone, there's some variation here. But this is a pretty typical series of events. Okay? Yellow part, right? We're moving strongly towards the positive, right? That gives us the big rise from Q to R. Okay, next one's a little bit tricky. See the vector there for the red part? It's headed towards the 2. What's happening here? Where is 2 relative to our axis? Is it headed towards the positive or the negative? Neither, really. It's almost perpendicular to that dotted line axis, right? Right. So here's our perpendicular line right here. Right. That's pretty much where it's headed. It's headed parallel to that, right? So we really don't see much here with that portion of the ventricle depolarizing, even though it's a huge part of the ventricle, right? It's just that it's moving, the overall vector is more or less perpendicular to our lead, right? Our axis. So what's going to happen is that the EKG wave just basically drops back towards 0, okay? And then what we pick up with the blue portion here, the last part, is that we're moving in the negative territory, right? And that's where the top of the ventricle is depolarizing. Okay. So if you imagine this sort of spreading out, we just sort of divided it randomly into 4 pieces, but it more or less corresponds to these EKG waves. That our QRS complex is a result of this movement of vectors in sort of 4 different patterns, right? Pointing towards 9 o'clock, 5 o'clock, 2, and 1. So whatever lead you're looking at, right? If you're looking at a lead across the body like this, right arm, left arm, you can still remember 9, 5, 2, 1 because that's not going to change, right? Now what's changed is your perspective. Okay. I'm not going to ask you test questions from that perspective, by the way. That'd be cruel, wouldn't it? Yeah.
So like what would be the benefit of using the electrodes to different parts?
All right, so let's say we wanted to, what she said, what's the benefit of moving the electrodes? So if we wanted to look at this perspective, right? So positive, negative, oops. Because we suspect there's a problem with the person's ventricle, right? Maybe they had a heart attack, and we're wondering if there's a loss of functional tissue in let's say the left ventricle, somewhere in that gray region, right? If we oriented the lectures like this, we could get a really good look at that electrical activity. Okay? Obviously, we need to know what that's supposed to look like, and then you could compare that to your patient. Does that make sense? So a lot of times, the different leads are used to detect different but sort of common electrical anomalies that point to problems in the heart, either conduction or death of contractile cells that leads to conduction problems. Does it make sense that if you have some contractile cells dying, that this would affect the electrical activity? Right. So if some of those cells die, these patterns are going to be disrupted. Right. They're not going to look the same. Because these vectors are summing everything together, right? And if you take parts out, it looks a little different. Okay, but that's what EKG is with regard to the ventricles. We haven't talked about repolarization yet. Repolarization happens both in the atria and the ventricles. Okay, and as we'll talk about in a second, that little bump at the far end, what do we call that? T wave. It's what's happening there? Ventricular repolarization. Okay. What is happening here in this ST segment? This, by the way, segments are just referring to the space, the lines between the waves. Okay, so QRS, S is at the bottom of that complex, and T wave. What's happening here electrically? Looks like nothing, right? What's happening to the heart during this phase? Yeah,
Atrial repolarization.
not quite. And I'll talk about that in a moment. It's not atrial repolarization. So what happens to your cardiocytes between ventricular depolarization and their repolarization? They plateau, right? So we can sort of superimpose, at least in time, that this little action potential we learned about is happening roughly in this same time frame. Okay? Now, yes, not all of our ventricular cells are depolarizing at the same time. We just talked through that, right? But on average, we could say that the depolarization phase is happening here. Repolarization phase is happening here, right? That means in between them, we have plateau. Okay. Okay, so this ST segment is kind of an important thing on an EKG because the length of that segment tells you about what's happening to the heart, right? A short segment means a short plateau, right? Long segment, long plateau. Okay. All right, let me jump to the last part of this ventricular repolarization. Okay. Now, it's a weird thing that you have to trust me. Okay. Nobody else that trust yet? Yeah, until the first exam. You'll not trust me. That's okay. But for now, we're good, right? This is a weird thing about the heart that has an explanation, but there's no why to it. Okay. In other words, why is it like this? All right. So the repolarization of the ventricles happens in a pattern that's shown here. Okay. What was the first part of the ventricles that depolarized? Do you remember? It was the septum, right? So over here, and then it was here, right? And then it was the walls, right? And lastly, over here, okay? So the pattern of repolarization, you might think, would follow the same pattern, but it doesn't. Okay? All of these cells have an action potential that looks a little different. Okay? So some have action potentials that look like we described. Others are longer. Others are shorter. Okay? And it's different throughout the heart. Okay? So what happens here with ventricular repolarization is that some of these cells that they just depolarized